We are continuing on to topic 2 of chapter 2, dealing with elementary functions, graphs, and transformations. You're going to find this to be useful as you continue your work in finite math. Now, here we see each of these functions can be expressed in terms of this function. I copied this right from the beginning of this section in our textbook on page 58. So let's look at it. Now, you need to remember that this is this. That this function of x is x squared. So in comparing this first one, here we're saying g of x is the function of x minus 4. Well, we just said that the function of x is equal to x squared. So this is x squared, and we just put our x squared and then bring down the minus 4, and we have this first function. So keeping in mind that f of x is x squared. Now in the second one, as we look at it, we're saying that this function is this, but we're saying that this f right here and f of x we said was equal to x squared. So this is going to be our x value. So we can then write it as h of x equals, now remember this stands for our x, and we would get x minus 4, the quantity squared. And that's where we are. And in this last one, again, we're saying that this is x squared right there. So this then becomes k of x equals, we just put a negative 4 in there. So we're doing some substitution, and that is basically what we've illustrated here, that each of these functions can be related to this, and we've shown you how it ties in. All right, now going on to example 1, we'll get to it in a moment, but I'd like to go over some of the basic functions that are called basic elementary functions. So here we have the function of x equals x. This is an identity. Here the h of x is x squared, which is the square function. And then raising x to the third power is the cube function. And then putting the radical sign over the x, which is now the radicand, that's the square root function. And then if our index number on the radical sign is a 3, then this is a cube root function. And then if you have vertical bars to either side of your x, this is the absolute function. So let's see this in action now with our example. So when we use the letter F of 64, the identity, by definition, is just going to be 64. Now, when we have this function of h, we're looking for the square of 64. And the square of 64 is a big number. It's 4,096. And of course, you could use your calculator for that. Now, the cube of 64 is even a bigger number, 262, 144. Now, for the square root, where we're right here, the square root of 64, you recall, is 8. 64 is a perfect cube, and the cube root of 64 is 4. And the absolute value is always its positive value, and that is just 64. So depending what number they're asking you to apply the basic elementary functions, these are the results. In your textbook, they do give you another example where they're asking you to do a negative 12.75 for all of these. And of course, you can use your calculator to do it. And in some cases, you're going to have to approximate because they're not perfect squares. And when you take the square root of that, keep in mind that that is not a real number. You can't have a negative sign under a radical sign whose index number is even. Okay, now we're going on to page 60. We're going to look at the graph of these particular basic elementary functions. Now, for an identity, when you have the function of x equals x, you end up with a line that runs through the origin. And keep in mind that all of these have arrows at the end of the line. So if we want to define what would our domain be, in this case it would be x elements, and this would come from negative infinity to positive infinity. That is all real numbers. Now for the range, this is coming up from negative infinity to positive infinity. And again, all real numbers. In this next one, keep in mind that this is x squared. This is just plain x. This is a parabola starting at the origin, but in terms of x values, this would eventually go to negative infinity to positive infinity. Now range, it only starts at 0, and 0 is included in the set, and then it goes up to positive infinity. Now m is the graph of x cubed, and again, there are arrows. And eventually, this would, for domain, go all the way to negative infinity to positive infinity. And that's the same for the range, y values. Now, for this one, it's the square root of x. And by the way, if you had a graphing calculator, you could put all of this in, and you would get these graphs. But for our domain here, it's starting at 0. and going on to positive infinity. And for our range, again, it's starting at 0, and eventually this is going up ever so slightly, but it does. So this would again be starting at 0, going up to positive infinity. Now, if you were to take the cube root of x, you end up with a graph that looks like this. And again, these are going off in this direction, and I probably should make that a little bit more like that. And as for domain, it's from negative infinity to positive infinity, and that applies to the range as well. Now for absolute value, we start at the origin, and on this way it goes all the way to negative infinity for x values, the same for positive infinity this way. But for our range, it's starting at 0 and goes to positive infinity. Now in this next part, as we continue with vertical and horizontal shifts and transformations to these basic elementary functions, we're going to deal with the first one first. Now, the graph of this, you may recall, was a line like so. Now, back in earlier chapters, we talked about this, y equals mx plus b. Well, if this is our line, and we're adding a constant to it, which is our, in the old days, was our b term, the y-intercept, that's going to shift. For instance, that would be 0. There wouldn't be anything here. This would be like plus 0. That would go through the origin. Once we add a constant k, whatever it is, if it were a positive 2, that's going to shift this line upward by a positive 2. And if it were a negative 2, would shift that line down to a negative 2. So basically it's the same line, but when we have it in this form, it's sort of like this. This is for our constant. If it's a 2, it shifts it up, transforms it up 2 units, and this down 2 units. Now, this next one, when we think of what's going on, again, our original line was like so, but now we're introducing a new variable that if this is an h, and it's a little confusing, but I'll give it to you, it's you move it the opposite sign of h. And I'm assuming we'll get to that a little later. But if h is let's say a positive 2, we're going to shift that actually to the left to a negative 2. And it'll look like that. Or if it is a negative 2, we're going to shift that to the right 2 units. Okay, well, let's explain why when you see the function and this letter H actually refers to the X-intercept, where the line will cross the X-axis. So if your basic equation is, as we see over here, y equals x plus 2, we know it's going to go through 2 there, and then what will be the X-intercept? Well, this is your y-intercept. Our X-intercept is this. So what is the value of A? -2. So if in your original equation you had a 2 there, you know that this is going to shift your line over to a -2. So it's the opposite sign of what you have there. And if your equation is x minus 2, again, your y-intercept would be here, but what would your x-intercept be? And it would be opposite signed, a 2. Okay, so a shortcut way is just when you see something like this, your graph is going to shift the opposite sign to that place on the x-axis. So if you have a +2, it'll be a -2. If you have a -2, it'll be a +2. Okay. Okay, going on now to example 2 on page 61. They're asking us to do some transformations. Actually, these are going to be vertical shifts. So if we were to plot this first equation, y equals the absolute value of x, we have this. Now, if we shift it vertically down 5, 1, 2, 3, 4, 5, then our line will be like so. If we move it up 4, shift it up 4, 1, 2, 3, 4, we then have our vertical shift by this constant, which used to be the y-intercept in a sense. Okay, now keep in mind from what we had done just a few moments before, here is our basic graph. Now, in this case, since it's included within that, this is our h value, which will be our x-intercept, and its opposite sign. So, this will be a -4. And that will be a horizontal shift to the left when that's a positive. And we proved that in our just a few moments ago. And then this one would be a horizontal shift 5 units to the right of 0. 1, 2, 3, 4, 5. Opposite sign, 5 units. And there we go. As we go on to our next function, here we're having the function is x squared. We get a parabola, and now we're going to shift it vertically up 2 units. And we get something like that. Here we're going to shift it down 4 units. And using the same graph, we'll make a new one. We're going to change this just a little bit, where we put this, take the square off of that and make that squared. And in this case, again, the first one is the same. But here, we're going to shift this horizontally 2 units to the left, so a -2. And a -4, we're going to shift 4 units to the right. And there we have it. So we have done a number of transformations, vertical and horizontal. This is the horizontal ones, opposite side. And again, it's like a recipe that you're going to, in a sense, memorize so that you don't always have to think about it. Now, theoretically, if you put any of these into your graphing calculators, this is what you're going to get. That's the marvel of those graphing calculators. Okay, we're now continuing, and we are still, well, actually we're moving on to page 63. And on this page, we're doing what is called reflections, stretches, and shrinks. Again, there's a lot of vocabulary going on. And they're asking us to relate this equation, y equals the absolute value of x, which is this black line right there, to y is equal to 2 the absolute value of x. Now when we plot that, we actually get this line, that our slope is actually 2/1, so we're going a little closer to the y-axis here. So what did we do there? Well, when we go from this position to a little tighter position, we call that a stretch. So the relationship of this to this equation, the black to the blue line, is a stretch. And when we compare it to this one, and remember 0.5 is like 1/2, that tends to broaden out, and that is this red line down here. In relation to this black line, the red line opens up more, we say it shrinks. So, a couple of things going on. And these are all, in a sense, since it's up and down, these are a vertical stretch from the black to the blue, a vertical shrink from the black to the red, and these are the equations that relate to. And then a little later on, they're saying relate the same equation where it's a -2. So this would be a negative slope going down this way, and the relationship of the green line to this blue line up here, we say is a reflection, and it is a vertical stretch. It's getting closer to the y-axis. That's a stretch. If it was getting further away from the y-axis, that would be a shrink. So a couple of words going on. And again, you can always relate to your textbook, reading over what they give you there. Okay, as we continue with this section, on page 64, we talk about combining graph transformations. So here we have our original, which is y is equal to the absolute value of x. And then we have y is equal, and remember, we could change these to function notation very easily. The y could always be substituted for the function of x. And then here we have a negative sign in front of our absolute value, and +1. So we know that this is going to transform it, that is, shift it, opposite sign, 3 units. -3 becomes a +3. And we're going to also shift vertically up 1 unit. So the point of this will be right there. And then we just do our lines opposite to this. So here is this graph. Here is this graph. We have combined graph transformations. And the nice thing about it is you get to see how things relate. Now, in a additional question that they gave us, for example 6, the one we just did, they gave us this graph, and they asked us to find out if this graph of function of x is x cubed is in the black line, what would be the equation of its reflection? Now, an interesting thing about reflections is that you kind of make like a little dotted line right here. And if you had a piece of paper, and I could recall when I taught high school geometry, we used to have these little, what they call patty papers, which were little squares that they used to put in between the hamburgers. And they're sort of clear. And if we had something like this, we would fold it in such a way that we would get the reflection of it. I didn't do that very well. And this graph is not perfect. The one in our textbook is much better. But what is the graph then of this reflection of this? And the answer is, well, since it's reflected, it's going to be opposite sign outside of the parenthesis. And notice that it's shifted 2 units over, which should be a -2, which becomes a +2 in our formula inside the parentheses that we're raising to the third power. And I did use my graphing calculator to check this. And if I turn it on and I say graph, again, there is our graph, which is what we had here. And these are the equations that I've put in. Okay, going on to our last topic of Chapter 2 that we'll be covering in Math 1127 is piecewise defined functions. I could recall years ago when I first saw this, I said, well, what in the world is that? Well, interesting, it's a piece of something, part of something that you're defining, and it is a function. So to give you some background, and again, this is in your textbook on page 65. Here is one that we see was y equals x squared minus 2. So this is going to shift downward to a negative 2. There's your standard parabola. Now this one is y equals, notice it's a negative x squared plus 2. So it's going to, because of the negative, it's going to open up downward, and it's going to peak at 2. So that's shifted upward from what we had before. And then this one is actually the same 2, but where we're not having this part or this part. We've only taken pieces of it. And that's where the piecewise comes in. Now, in this one, which is your upward opening, we're saying that x is greater than 0. So our x values will be greater than 0 and will be going up this way. This, by the way, is a qualifier, we call it. And then here, for our downward, we're saying that the values of x are greater or equal to 0. So it gives us this. Now, because of the inequality sign, where we have it equal to something, where it starts makes a dot there. This one, because of the inequality sign not having the equal in it, 0 is sort of where it's hooked onto, but is not part of that set. And we indicate that on the graph by putting a hollow there. Now, if we were to apply the vertical line test as we moved over this, is this a function? And the answer is yes, it is a function, because when we get to this point, since this is a hollow, this one's a solid, the vertical line is only going to be intersected in one place for all of them. So this is a function. And later, I don't know if they're going to ask you to actually graph some of these, possibly. We'll show you the technique for doing this. For example 6 on page 65, it is rather a bit wordy, and what I did is I reproduced the graph, and I don't know if you can realize what you're seeing here, but this is a gas company that's going to sell cubic 100 feet of gas, and that for initial purchase, the price of the gas is quite expensive. And that would be for those home users that don't use a lot, but you know, they have all this overhead and whatnot, so they have a rather expensive price. But then when you reach a usage of greater than 5 of these cubic 100 feet, the price gets a little less. And you can see that the slope of the red line is dropped down a little bit. It's not quite so steep. And then finally, once you get to 40 cubic 100 feet, the price is even less steep. And that's what is illustrated here. And they do give you formula for each of these lines, and they give you the qualifiers. Again, we don't want to make the tape too long. This is all in the book. And if you have a problem like this, again, your reference, you have the tutorial bars, help me solve the problem. And if you still have a problem, bring it in. Here in Math Lab, we're happy to help. So this will wind up this lesson.